First, there was nothing. Then, there was area. Hello everyone, I'm Sam.
And I'm floating in outer space.
No, your name.
Peter. I'm Peter.
Today we'll be talking about area and its applications to calculus. So let's start off with the basics. What is area? Peter?
Area is the two-dimensional space between lines, often represented with length and height. This can be anything from the surface area of a square to the cross-section of an apple to the size of a piece of paper.
That's right. Today, Peter and I are applying this to astrogeology. Peter, grab a sample for me, would you?
Sure thing.
Now let's take a closer look at this. System, activate hollow screen. Scan for equations matching the outline of the maximum cross-section of the rock. So what we're seeing here is that the rock is bounded by a straight line on the bottom and a semicircle best represented by the equation 4 equals y squared plus x minus 2 squared. Would you like to solve this one, Peter?
Sure. So remember the integral thing you learned? Well, finding the area under a curve is a simple application of that. In this case, we have our bounds at 0 and 4. We know that because it's where the two graphs meet. So what we do now is set up an integral. Since the bottom of the rock is a straight line, we can just make that the x-axis. From here, it's pretty simple. Since the bottom bound is just the x-axis, we plug our equation into the integral with the above bounds. With that, we found that our area is about 6.2831 inches squared. Another way to look at this is finding the area of a semicircle. In that case, we know the equation is 1/2 times pi times r squared. Plug in 2 and we get 2 pi.
Thank you, Peter. Great explanation. Now how about you grab another rock for me?
Sure thing.
System, scan for equations, please. Okay, so here we've got the lines 3 times root x and 1 over 60 times x minus 1 to the 4th. Now, while this may look a little harder than the previous one, it's actually quite simple. What you're essentially going to be doing is subtracting the smaller area from the larger one, creating a cross-section. In this case, we start by finding the points of intersection. You'll probably need a calculator for this, and you can use the graph's intersect function to find it. Our points of intersection here are x equals 0 and x equals 5.537. Now let's take the integral of the top line. When you plug it in with those bounds, you get 26.0580. On to the bottom line. The integral of that will give you 6.4113. Now to find our area, all we have to do is subtract the two. And that tells us that the area of our asteroid here is 19.6467 inches squared. Okay, Peter, how about we give them one to try before we get back to work? Peter, watch out. There are some bigger asteroids coming our way. System, get a lock on his location, quick. Well, shoot. Guess his beacon broke too. I'll have to search for him manually. Hey, would you like to help me out with this? System, pull up the bounds of the minimum and maximum trajectory Peter could have taken, please. Okay, so at his speed, he'll be entering the gravity field of a very large nearby planet in about 45 minutes. The planet's about 50 miles away. How about you pause this video for a second and solve this, and we can compare notes. Okay, so when solving this, I know that it's going to be really similar to that first rock we went over. His maximum trajectory is a straight line, so we can just set that as our x-axis. From there, you just identify your bounds and set up your integral. In this case, I found our bounds to be 0 and 50, because I know 50 is the maximum distance he can go before he faces certain doom. And when I plugged it all in, I found that I have to search 707.1067 square miles of space in the next 45 minutes to find Peter. Hey Peter, are your comms still active?
Yeah, I just floated into some sort of giant asteroid.
Well, I tried applying area to find you, and according to my calculations, you're doomed.
Why don't I just tell you what's around me? This asteroid is relatively hollow in the middle, but it's got 3 big entrances to it.
Oh, I see it. I don't know which one to enter, though. Could you use your suit's computer to figure out which opening I should use?
Sure. Computer, scan the X's for matching equations, please. Okay, so our ship has a maximum height of 15 feet, a maximum lower width of 10 feet, maximum upper width of 5 feet, and a maximum area of 100 feet squared. The dimensions of the opening need to be at least half a foot wider than these dimensions for a ship to fit. Why don't you take a second to solve this? Okay, so the first thing you're going to want to do is grab the area of everything. For entrance 1, the area is 105, founded by calculating the area of a trapezoid. Entrance 2 is founded the same way as we did the first rock, which gives us about 168. Entrance 3 is found the same way we found the second rock, by taking the two integrals and subtracting the bottom from the top, and it gives us 150. So now we know that all three holes have proper area, but that doesn't mean our ship will fit through all of them. Entrance 1 has an upper width of only 3 feet, so our ship wouldn't fit through there. And entrance 3 has a total height of 15 feet, which with our height requirement makes it impossible for our ship to pass through. That leaves us entrance 2. This one works because it has the area we need, as well as the upper and lower width and height.
Hello, Peter. Why don't you head back inside to decompress? Well, it looks like that concludes our adventures for today. Thanks for tagging along. We'll see you next week on Peter and Sam's Calculus Adventures.